On our final set of exam questions, we are going to look at 3 of them regarding collisions and momentum. The first of which is from a spring 2022, question paper 42, and is the first question. Small smooth spheres A and B of equal radii and of masses 5 kilograms and 3 kilograms respectively lie on a smooth horizontal plane. Initially, B is at rest and A is moving towards B with speed 8.5 meters per second. The spheres collide, and after the collision, A continues to move in the same direction but with a quarter of the speed of B. Find the speed of B after the collision. Okay, diagram. Let me put it there. Actually, I didn't put a diagram. Basically, the formula is self-explanatory. If you put the information like this, you have the masses, you have the initial speed, you have the final speed of A as a relationship, as a function of the speed of B. I'm using speed, I should say velocity, because in momentum, you are using velocities, not speeds. So I'm going to start using velocity instead of the word speed, because the direction matters, and it matters a lot. Okay, so the velocity of A is 1/4 of the velocity of B. If you just use the law of conservation of momentum, you'll get what you want. The initial momentum total equals the total final momentum. The total initial momentum is due to both objects, so you have MAUA. No, it's not. It's due only to the first object, object A. Object B, the initial velocity is going to be 0, so the total momentum of object B is going to be 0. But then, after the collision, they are both going to move, and you can put the velocity of A after the collision as a function of velocity of B, so 0.25 the velocity of B, all right? And you will have just an equation with one unknown that will allow you to get the velocity of B, that is 10 meters per second. Then you want to calculate on the second sub-question the loss of kinetic energy of the system due to the collision. Here I made already a very big shortcut in terms of factorizing, but this is just applying the formula for the kinetic energy before and after. After is the kinetic energy of both objects. Before is the kinetic energy of both objects before the impact, knowing that one of them is going to be 0. Okay, so it's going to be 1/2 of MAVA square minus 1/2 of MBVB square minus, open brackets, 1/2 of MAUA square plus 1/2 of MBUB squared, close brackets, okay? Factorizing this, the whole thing, this is what you'll get. Now just substitute the correct values. Don't forget that V stands for final velocity and U stand for the initial velocity. This one, as you know, is 0. Substitute and you get the total change in kinetic energy. You already been told that it is a loss, so you just need the magnitude. It's 15 joules. Simple enough. Spring 2022 again, but now it's variant 43, still question 1. Two particles P and Q of masses 0.3 kilograms and 0.2 kilograms respectively are at rest on a smooth horizontal plane. P is projected at a speed of 4 meters per second directly towards Q. After P and Q collide, Q begins to move with a speed of 3 meters per second. Okay. If they are at rest on a smooth horizontal plane. What is the situation that you have? I already represented it here. I'm sorry. I have already represented it here. Okay. So you have the mass of both objects, P and Q, the initial velocity of P, the initial velocity of Q. The final velocity of P is what you need to know. The final velocity of Q is 3 meters per second. Again, it's just applying the law of conservation of momentum. All right? Substituting each one nicely, keeping the only thing that you don't know as your variable, and solve it. There's no big deal over here. Then after the collision, Q moves directly towards a third particle r of mass m kilograms, which is at rest on the plane. The two particles Q and R coalesce on impact and move with a speed of 2 meters per second. Find m. This is too slow. Give me a second. So all the relevant information is here. The mass of Q, the mass of R, the thing that you need to calculate. Now, the initial velocity of Q is going to be 3 meters per second. The initial velocity of R is 0 meters per second, is stopped. They coalesce, so this means that the final velocity of the set is 2 meters per second. Knowing this, you can apply again the same formula, the law of conservation of momentum. After the impact, you can put the whole thing as a single object with a combined mass and the same velocity, all right? You are going to calculate the mass of R using this part over here. This one is going to be 0. The initial momentum of R is 0 because its velocity is 0. But here you have the unknown. After substitution, you get the value of the mass of R as you were asked. It's very simple questions, these two. They were the first question, usually the first question on a paper, particularly in a mechanics paper, is the simplest one. It's just to start getting used to the exam. This last one is also from 2022 paper, but it's variant 41. So they are all from the same year and same season. This one is from the 41 variant, and this topic would appear this year on the last question. So much more complex, not this one, but this one, as you're going to see, this is as complex as it gets, and I put this on purpose also for you to know that in the same season, different variants can have different structures, all right? So question 7. Two particles A and B of masses 0.4 kilograms and 0.2 kilograms, respectively, are moving down the same line of greatest slope of a smooth plane. The plane is inclined at 30 degrees to the horizontal, and A is higher up the plane than B. When the particles collide, the speeds of A and B are 3 meters per second and 2 meters per second, respectively. In a collision between the particles, the speed of A is reduced to 2.5 meters per second. Find the speed of B immediately after the collision. Okay, you have a collision on a plane that is going down, but the law of conservation of energy on the impact is still going to occur. So this is before the impact, they are about to collide, and here they are after the impact. All the information is here, the masses, the initial velocity of A, the initial velocity of B. Obviously, the velocity of A must be bigger than the velocity of B, otherwise they would never touch. And here you have the velocity of A. The velocity of B is the thing that you need to calculate. Just apply the law of conservation of momentum again. All right, you have everything but the velocity of B. Substitute the things. Everything goes in the same direction, so you don't have to worry about pluses and minuses. You can put everything as positive being down. And you have the velocity of B. The question that interests me is the next one, which is worth 7 points, if I'm not mistaken. Yes. All right. After the collision, when B has moved 1.6 meters down the plane from the point of collision, it hits a barrier and returns back up the same line of greatest slope. B hits the barrier 0.4 seconds after the collision, and when it hits the barrier, its speed is reduced by 90%. The two particles collide again 0.44 seconds after their previous collision, and they then coalesce on impact. Show that the speed of B immediately after it hit the barrier is 0.5 meters per second, and hence find the speed of the combined particle immediately after the second collision between A and B. Okay, it seems a lot, so let's break this down into smaller steps. It combines the topic of collisions, of momentum, with the topic of kinematics. So you have to have these two, you have to deal with these two at the same time. So what do you have? Let me go over here. Okay. You know that the distance between the first impact and the barrier is 1.6 meters, and you know that the impact of B on the barrier occurs 0.4 seconds later. All right, I have here all the information. You know that the speed of B is reduced by 90%. This means what? This means that the speed of B after the impact is just going to be 10% of what it used to be. So the velocity of B over here, the VB, is going to be 0.1 the UB. Okay, what is this UB? Is the speed just before the impact. Make sense? All right, so we need to calculate that value, how much that is. So for B, let's calculate first the speed just before it hits the wall. And for that, you may just use this UVAT formula, V equals U plus AT, now adapted to this situation. The UB2, which is the velocity of B just before the impact, equals the UB1, which is the velocity of B when it hit the particle over here, the situation described above, plus AT. What is the A? After the impact, the only acceleration that is going to be applied to the object is the horizontal component of G, right? That's what is speeding up the ball down the plate. After the impact, the ball is still going to accelerate downwards, but because of G, right? Not the full extent of G, because it's on a plane, but the horizontal component of G, which is given by what? Is given by 10 sine of 30. I made here a very tiny diagram. This is now the G. This is the horizontal component of it. So it's G sine of 30, which is 5. Okay? You know the time. It's 0.4 seconds. So you have everything. The speed of B just before hitting the barrier was 5 meters per second. The speed when it comes out of the barrier is going to be 0.1 times that, which is 0.5 meters per second. So the first part of the question is answered. Now, the second part of the question was asking you to calculate what? It was the speed of the combined particle after they coalesce. What is happening over now? B hits the barrier and goes up, but A is still going down, so eventually they are going to hit again. And this happens 0.04 seconds after B hit the wall. This happens 0.4 seconds after the initial collision, and the second collision occurs 0.44 seconds after the first one. So if it took 0.4 seconds to hit the wall, then it takes 0.04 seconds for the second collision. Make sense? So 0.04 seconds after hitting the barrier, ball B is moving up the plane with speed. What speed is it going to be now? It's going to be given again by the law of, by the same Suvat formula. Now, the velocity of B, 0.04 seconds later, is going to be the initial velocity, which is now going to be the one that we just calculated. Now, minus the acceleration. Don't forget that now the gravity is trying to slow it down. It's going up, so it's going to slow it down. Hence, this minus over here. And what time are we talking about? We are talking about 0.04 seconds after hitting the barrier. So the circumstances are now, we are dealing with the physics after hitting the barrier. So these are the circumstances. We can calculate this velocity as being 0.3 meters per second. So on the moment of the second impact, VB is going up the plane with this speed. What about A? A is simpler, the motion, it was still going down. 0.44 seconds after the first collision, A is still going down. With what velocity? Again, is the same expression. The velocity of A just before the second collision equals the velocity of A just after the first collision plus the horizontal component of G, right? The component of G that is still accelerating it down the plane, times the time for which it was moving, which is 0.44 seconds, right? So substitute the whole thing, and you have the speed of A, which is 4.7 meters per second. All right? Now, don't forget that these are speeds, okay? Not the velocities. So let's choose down the plane as a positive direction. Now we just apply the law of conservation of momentum again, and you have MAUA. Don't forget that UA is this 4.7 plus MB VB, just to use the same expression that I used before, which is going to be a negative value. This is a minus, this is a negative velocity because I chose positive as being down. And as I told you, B is now going up, all right? So the whole thing, this term over here is going to be negative, all right? Equals the mass of both put together because they coalesce times the velocity that you need to calculate, right? So the velocity equals this, which is that, divided by the combined mass, which is 3.03 meters per second.